Good morning, drone pilots. Today is going to be the hardest and most important lecture of the entire quarter, because we're going to have the most math and theory, and we're going to have the most important practical discussion of preparing for flight. Now, my video recording has failed, so I'm going to stop it every 10 minutes so I don't lose the entire lecture. So let's get started. So last week's video was not up. Okay. So as I've mentioned, you've done the hardest hardware part with all the soldering. That's done. You've done the hardest software installation part with all the radios. That's done. So the rest of the practical part is assembly and flying. So today we're going to discuss the details of preparing for flight and the theory of feedback. So it's two very different important theoretical topics. One theoretical, one practical. So these are things that you have to do to prepare for flight. Calibrate the radio control, calibrate the accelerometer, calibrate the compass, optional, calibrate the current and voltage meter. You need to understand the flight modes. You need to understand the fail-safe behavior. You need to understand the tune. You need to understand the way waypoints and auto takeoff and auto land work. You need to understand guided mode, and you need to understand geofence. So that's the topic of today's lecture, is going through all those in theory and in practice. So the calibration, let's do that first. So I guess I can end the show, and we can go ahead and calibrate the drone. So I'm going to walk you through what you have to do to calibrate everything.
Hey Peter, welcome back. Disarmed.
So we have the radio. And the camera's not that important at this point. It's more for demonstration purposes. So the camera, and you do this with the props off. So there we are, booted.
Telemetry connected.
And what's the first thing that we want to calibrate? The radio. So I'm going to go to Mission Planner. Takes a moment to get everything ready. Oh, I have to plug the drone in, of course. So I'm going to use the USB connector that's connected to my laptop. Make sure it's a data cable. If it's just a charging cable, it won't work. And now we should be able to connect to Mission Planner. So just to be sure, let me check something. Yeah. I can go to Device Manager. Look at the COM ports, and there we are, ArduPilot COM3. So we're good to go on COM3, connect.
Mode change to RTL.
RTL.
Mode change to stabilize.
So the radio calibration is here, and the way you do it is you click Calibrate Radio, and then ensure your transmitter is on, click OK, and then you wiggle all the sticks, and it determines the max
Arm, fence requires position.
of all of your
Mode change to RTL.
inputs.
Mode change to stabilize.
Now,
Arm, fence requires position.
yes, thank you. So you'll notice, for example, the throttle there, the lower end is 989, the upper end is 2002. And that's from the old-fashioned days of PWM. where the pulse width modulation was the protocol, and 1 millisecond or 1,000 microseconds was zero throttle, and 2 milliseconds or 2,000 microseconds was max throttle. But the circuits never were perfect. So the circuits sometimes gave you 2002 microseconds instead of 2000. So that's why we calibrate it. That's less important in autonomy, but if you ever fly where you really care about every last 0.1% of the end of the range, you calibrate the radio with like that. So for completeness, we calibrate the radio. So we're done, and here's the min-max that it found. One small piece of advice is that the trim, here's the throttle. I can bring the trim down.
Minimum trim reached. Trim center. Minimum trim reached.
So there's a trim on all 4 controls. So for the purpose of this class,
Trim center.
I would suggest keep them centered on your radio. And you won't really need to worry about it because it's autonomous. It has stabilized mode. But the throttle is one special case where sometimes the throttle isn't quite at zero when the radio turns on or when the drone turns on and the software gets upset. So you might have to trim it. You might have to use the trim to bring the throttle slightly down, because for safety, it doesn't like to arm when the throttle is not at zero. So that's the first calibration. The next one is accelerometer. So this is simple. Which way is up? Okay, so when I move the drone around, you need to calibrate which way is up. And your flight controller may not be mounted perfectly flat, etc. So the way that's done is you go to Setup, Accelerometer Calibration. And there's 2 that you can do. One is level, where you hold the drone level. And now I'm going to regret this because I'm not doing it quickly. And it calibrates level. And then the next one is you calibrate everything.
Place vehicle level
So
and press any key.
You have what it
Place
does
vehicle
is
level and press any
calibrates
key.
X, Y, and Z. So you put it level, press a key. And then it says place vehicle on left. So you have to place the vehicle on its left side. And the more accurate it is, the better. So I'm doing it quickly as a demo, but you want to find something that's square. Find a flat table, find a book. You can use the side of an oscilloscope, anything that's square, and do your best to get it exactly on the left side. And you do that with all the orientations. Now I have to put on the right side. And so on. And that's done. Nose down. Done. Nose up. So this is going to be a horrible calibration because I'm doing a real quick and dirty job.
Calibration
So
successful.
I'm going to recalibrate it carefully.
Calibration successful.
So that's the accelerometer. Now, your parameter file will change. So if you download the parameter file from Canvas, you're using the calibration that I did when I calibrated it a long time ago. So always save a copy of your parameter file after you've done a calibration to disk as a backup. Compass is the most difficult one. In practice, it's most difficult. So, like I said, compass allows you to determine, we can go back to Mission Planner, and I can pick up a picture here. Probably do it in picture. So you can see on the top, when I rotate it, it tells me the direction east and west and whatnot. Okay, so that's being done by the compass on here measuring the magnetic field of the Earth. It's just like a compass you have when you're hiking where there's a needle that moves and points north. So it's on this chip, it's detecting the magnetic field. That's why there's this standoff. Because last year we had that GPS and compass mounted right here, and when you throttled up, the current created a magnetic field that was larger than the magnetic field of the Earth. And it was really difficult to get the calibration working, even when the current wasn't there. So make sure you use this standoff there in the lab. Okay, so the compass calibration is, where'd it go? Here, and what you have to do is rotate the drone around.
Compass calibrator, cannot start compass thread. Compass calibrator, cannot start compass thread.
Okay, there's a problem. Okay, let's see. Well, it's still working. Okay, so there's an error, there's a problem there, and I forgot what it is. So I will solve that later offline. We had it last year and I forgot what the solution is. It's something to do with memory. But when it's solved, you have to rotate it around the roll, pitch, and yaw several times. And it will correlate the compass measurement with the accelerometer measurement. And then it'll have a calibration of the compass XYZ versus accelerometer XYZ. So as you see, things don't always go according to plan, and even now there's a problem. But I guarantee you, if you don't have the compass far away from the motor, there's gonna be a lot more problems. So that's calibrate compass. Now, the next one is calibrate current and voltage. So in your flight controller, there's a 50 milliohm resistor. There's a 50 milliohm resistor, and that's how you determine the current, is the voltage drop across that 50 milliohm resistor. So you can see the resistor right there. That's or 25 milliohms, even smaller. So if there's 1 amp going through there, how many volts are there? There's 1 amp going through a 25 milliohm resistor. How many volts are there across that? V equals IR. 1 amp, 25 milliohms. What's the voltage? 25 millivolts. So it's 0.025 volts. Now, in a typical op amp, you'll have an offset of 1 millivolt. So an op amp tries to make the output adjusted so the inputs are at the same voltage, but it's not exactly perfect. So most analog circuits have offsets of 1 or 2 millivolts. So if your offset is 1 millivolt, then you're going to be off by some number of amps, and it could be positive or negative. So you might go to the on-screen display and you'll see negative current, which is just because the circuit is not perfect. So there's a way to calibrate that. Now you don't need to, but I'm giving you it as an option. And so the way that this works is this is the microcontroller. It only measures voltage. You can't put 10 amps through any of these pins on the microcontroller, you fry it. So it's measuring the voltage drop across that resistor. And there's also, so there's an offset. And there's also a slope. That resistor is not exactly 25 milliohms. It may be 24 milliohms. So there's a procedure to calibrate it, which is dangerous. You have to have an external current meter that measures the current accurately, that goes between the battery and the drone. And then you have to throttle up to full throttle on the bench with the props on and measure the real current with a calibrated current, and then measure what the measured current is on ArduPilot, and do that at a couple different throttle settings. And then you fit a curve to that, and that gives you the slope, which is the resistance, which is not exactly 25 milliohms, and that gives you the offset as well. And if I look at power meter drone, there's one in the lab. It looks like this. So it's useful for all sorts of things. So it measures the actual current flowing through here. These are Dean's connectors, so you'd have to change it to XT60. And that allows you to measure the calibrated current, and then you compare that against what ArduPilot tells you. And then there's in Mission Planner, there's a setting, config, which has to do with the current offset and there's a setting, I forgot what it is, current. Okay, I'm not going to Google it. What I'm going to do is I'm going to look at, I should post it on our Canvas website. So last year, we created a file that explains how to do it. Let's see if I can find that file. No. Calibration. Oh, well, here's a calibration file that explains accelerometer. But that's not what we want. We want the battery calibration file. Current calibration. So here's the math. Okay, so bat amp per volt is one of the parameters. Bat amp per volt. So I have it set at 43.65, which is the number of amps that a 1 volt reading will give you, which seems wrong. It should be 25 milliohms. Let's see if we do, but it's amps per volt, right? So you have V equals IR. So it'll be 1 over 40. So it should be 40 if it's 25 milliohms. And mine is 43. So it's my resistance on my drone is not exactly 25 milliohms. My resistance is 23.2 milliohms. So this file on Canvas shows you how to get that, and then there's the offset also, which I have ideally 0, so I have it as 1.3 millivolts. So your drone will be different. So you have to run the drone at different currents and make a table of calculated versus actual, and that'll give you the slopes and the offsets. And here's a procedure, a step-by-step procedure for how you do that. Okay, we use ChatGPT for that, or you can figure it on your own. Okay, so this is optional, but if you don't do it, your current is going to be wrong. It's not really critical for flight. Yes?
I have two questions. The first one is that they assume the voltage is proportional to the current consumption.
Right.
So that's how they calculate the current based on voltage, right?
Right.
And another one is where is that?
Well, I can answer the first one if it comes back to you. So they're assuming V equals IR, which probably is very close to being true for this device because it's a big resistor.
Why do they need that big resistor?
Because it's dissipating a lot of power. You have 10 amps going through there. If you made it a 1 ohm resistor, you'd have 10 amps, you'd have 10 volts. It'd be I squared R, it'd be 10. It's in series. So the current comes in through battery plus through there and out to the motors. So you missed that part of the lecture, but we spent a lot of time soldering that. And not all drones have that capability. Most don't, because it's a luxury. And this is one thing I like about this flight controller. So I like it. But and we showed in the battery lecture, the battery voltage does not give you the instantaneous state of how much gas you have left in the tank. It's the integral of the current DT that tells you how much you've used. And then you can figure out how much you have left. So the battery voltage changes depending on the load, and even the battery voltage doesn't change very much depending on how much you've used until the very end. So this is a nice feature that they have. And The V equals IR is probably true, but it can't be a big resistance because it'll be too much power dissipation. So if it's a 1 ohm resistor and you have 10 amps, then it's I squared R is the power. So you'd have 100 watts in that little tiny resistor, which is probably more than you want to provide. Well, you'd also lose, if you had 10 amps flowing through a 1 ohm resistor, you'd have a voltage drop of 10 volts, and you only have 7.4 to begin with. So you want a tiny resistor. So, but because of that, the offsets in the imperfections in the readout become important to calibrate out. But it can't be, it's got to be tiny in value, but it's got to be big in size because it's got to be able to handle all that current. If you buy a 25 milliohm resistor that's a tiny, tiny one, it'll burn out. So it's got to be a big resistor. That's why, look, that resistor is bigger than almost any other components. By the way, here's the video chip that I told you about last week, the Max, it's analog now, the one that does the HUD on it. Okay.
Another question is, can I use a...
So you already told me what a good way of adjusting the P term, the proportional term is, in order to minimize oscillations. It's make that smaller. Just adjust the gain term and bring it down. And you can do the same thing for the integral and the derivative gain terms. And you can plot mathematically and analyze it in classes how it looks. And there are optimal values for that depending on the response function of your system. So it turns out that ArduPilot devs are quite intelligent. And they first of all have the P and ID terms suggested for small, medium, and large drones. So they're in the interest of time, we won't delve deep into that emission planner, but there's a config term, extended term here, which has the PID for roll, pitch, yaw, velocity, throttle response. So you also may want a particular velocity response. So there are multiple PID loops within ArduPilot, and you can tune all the parameters in Mission Planner. So they have a wizard that suggests the setup for small, medium, and large drones. Because small drones are very responsive, large drones are very slow to respond. However, you don't know. So it's even better. It has this great feature called auto tune, where it will actually measure the response function. So you take it up in the air, and this is one of the flight modes, and it will give it a sharp impulse response and measure how long with the accelerometer it takes to get to where it wants to go. And it'll do all that in X, Y, and Z. It takes about half an hour or 20 minutes. And each time it adjusts, it measures the response rate, adjusts the PID, and then it gives it a new pulse, and it does this in yaw, pitch, and roll, and eventually you get a nice tune. So I did that with my drone, and I'm giving you the parameters. They should be pretty close to the same for your drone. And that's a beautiful feature of ArduPilot. Last year, the stock parameters that we used for the small drones did not work because you would take it off and it would oscillate, and it would almost not fly. It was feedback. So there's also a suggestion in ArduPilot to manually just cut all the gains. So cut all the gains by half. What's the bad news if we cut all the gains by a lot? What's the negative?
It feels lucky.
It'll take forever to get there. If you make the gains really low, it might take 10 minutes to get to where you want. So it's a trade-off. We don't need to watch the whole video. Now, there is one more theory, which is Kalman filter. So somebody asked about what it uses, GPS or barometer. So it uses all of them, but it can't use the instantaneous GPS. Because like I said, for any given, you get one measurement per second with a GPS. And 50% of the time, it's within 1.5 meters of correct. 50% of the time, it's outside of 1.5 meters of correct. So what that means is that if you have a drone sitting on the ground, not moving at all, half the time the measurements are going to be 1.5 meters away from the other half of the measurements. So the GPS location will be jumping around every second, even though the drone is perfectly still. So you can't have a feedback loop that uses that state estimate, just the GPS. So all sensors are noisy. So Kalman filter is a theory that takes the noise and averages it out and does it for all of the sensors that you have. And it provides what's called a state estimate of the system. And there are weights for the different components that you can use that are tunable in ArduPilot. I've never had to mess around with them much, although we did for the flyaway. And the ArduPilot developer helped me with that. So that is column on filter. So that's also built into ArduPilot. Basically it's a moving average of all the sensors to give you what's called altitude heading reference system. So your location that the ArduPilot thinks you're at is not the instantaneous GPS location. It's not the instantaneous barometer location. It's some time average of all those. So you asked what a gyroscope, accelerometer, compass, GPS, barometric pressure. Some of them have airspeed. You're going to have LiDAR. You're going to have optical flow, all those, and anything else that can all be integrated in. So that's the other theory. Okay, theory over. 10 minutes left of the other flight modes. Let me see what we have left for the modes. Okay, what I'd like to do is use the whole time and get through everything. So, like I said, there are other flight modes. One of them is land, where it just goes into land mode. So there's a preset land velocity, which is in the parameters, just use the default, and it'll just land where it is. There's auto mode, where it'll do a waypoint mission. So if you put it into auto mode, it'll start flying to all the waypoints that you have pre-programmed. And then there's guided mode, where you click on a map, it'll fly there. So these are some of the interesting autonomous modes that you can use. They won't work with the controller. So when you do your final mission to get credit for this class, you're going to have to use the mission planner to set it into auto mode. So you pre-program the waypoint into the drone, and there's a video on how to do that. It's pretty easy. You click on the map, upload it, make sure you get it right, so it doesn't fly all the way to Timbuktu. But if everything's correct, then you press auto mode and arm it, and it'll automatically take off, fly the waypoints, and land. So the only way to get it into auto mode is to do it through Mission Planner. And that's your goal for the class. Guided, you just click on a map. So if you're connected on Mission Planner, you can also just click on the map and it'll fly there. It's a pretty neat feature. So you click on it, fly to here, you tell it the altitude to fly to, and it goes there. So Jack was asking, why do you have all these radios? I really like Mission Planner. I like the autonomous nature. Some pilots like just to fly manually, so you do you. Geofence, let's see how many slides we have left. Yeah, the geofence, and then we're going to do the checklist. So I actually have 9 minutes. I'm going to use them all. So geofence is what it says. You draw a fence, and if the drone goes beyond that fence, it automatically takes some corrective action, which is predefined by you.
Transmitter battery low.
So if it, okay, I don't think we need the drone anymore.
Receiver still connected.
We'll just
Fence breach max salt.
You need
Error
to
POS
define
vert
the
variance.
geofence before you fly. I require that as a safety measure. And the flyaway that we had, the students told me that they had a geofence, and I looked at the log files and they did not have it enabled. So we have to be pretty strict about that. Make sure it's enabled. And that way, if the wind blows it away, or the radio control gets lost, or it's programmed wrong some way, then you can have a geofence. And I have it set to auto land. So if it goes to geofence, it'll just land. And then you go get it up. So make the geofence within the arc. And there are a couple of videos on the geofence, how to set it up. Now, I told you how to fly in the cage. Let me teach you how I want you to fly at the arc when you do your missions. And let's hope that we have time to do this, because it's very important. And maybe I'm going to tell you this 3 times in a row, because it's so important. So it's a checklist. And I've created this pre-flight checklist for you in response to having taught this course several times and seen things that can go right and go wrong. So the first one is, before you come out to the arc, have all these things done. have the batteries charged, make sure everything is screwed on tight, etc. Two pages of it. So we're going to go over that in a minute. And then the day of the flight, this is a safety protocol. This is the crew briefing. And then I want you to each sign your name, what your role is. And then these are your missions. Take off, loiter, arm and loiter, check the RTL, check the fence, and then do your waypoint missions. So since we have about 6 minutes, let's go through the checklist in more detail. So before you come out to the ARC, one of the reasons we may not have a lot of time this year at the ARC, we'll see how much time they give us. It might rain. So if it rains, we can't fly. So I can't guarantee the weather. So make sure that when you come out, you don't have to spend an hour or two fiddling around. It's ready to go. So do it. And it's also hard to do troubleshooting out of the field. It's sunny, it's windy. You can't read the monitor on your screen. So it's really hard. So charge all the batteries. Do a mechanical inspection. Confirm your compass calibration. Confirm the accelerometer calibration. And check each one of these on a piece of paper. And then make sure you prefetch the map, because if there's no internet, you won't have the map. And then these are the parameters. Arming check 1. Battery low voltage 6.1. EK glitch radius 0. This will minimize the impact of vibration on drone position estimate. And it will lower the impact of IMU errors on the EK3 position. This is what Tridge, the lead developer, told me to do. Because we have super high vibration drones. They're tiny. These are the smallest RG-Pilot drones ever made by humankind. Most of RG-Pilot drones are way bigger. And I'm the only one, as far as I know, that's making these teeny tiny ones at any scale. So RG-Pilot got confused because of all the vibrations. That's another reason you guys don't like that sticky tape, but it's really soft. It's a nice vibration isolation between the accelerometer and the propellers. And what we think happened with the flyaway is there was too much acceleration, too much vibration of the propellers. It translated into the accelerometer and got rectified and down converted, and that confused the height estimate. So when it thought it was going down, it was actually going up. So it gave more throttle, and the feedback loop was unstable because of mechanical malfunction. Return to launch altitude 15 meters. Check the units. Fail safe throttle enable always land. Fence enable on. Fence alt max 25 meters. So if it goes above 25 meters, that's also a geofence breach. Fence action, always land. Confirm the fail-safe behavior by turning the radio on and then off, make sure it goes into fail-safe. Enable sound and mission planner. This is part of your radio checklist. Turn on sound all the way up on the laptop. Make sure you set up the FPV video, which we talked about. Set up the waypoint mission on the bench. Don't go out there and set the waypoint mission up. And there's a video on that. Set up the geofence on the bench. And then, okay, we have 4 minutes left. I need them all. So the day of the flight, check everything out of the field. Be ready to disarm at any moment. Do not hesitate. If something goes wrong, just immediately disarm. Period. We'll figure it out later. These are the crew roles, which we'll get into later in the interest of time, because I want to also do the arming. Okay, so, and then you do your missions, which we'll skip for now in the interest of time. We kind of introduce you to it gradually. So one thing I want to do before the end of the lecture is talk about the arming conditions. So I do need the radio.
Welcome back. Disarmed. Return to home.
Another thing, Tridge was quite upset with me because I had disabled all the arming checks. And he said when they get log files, they just...
Mode change to stabilize.
Somebody says, can you help me diagnose
failed to load font 1.
my problem?
Mode change to RTL.
And here's my log file. And if he sees in the log file that they have the arming checks disabled, he gets mad and throws it in the trash. Because they spent so much time on all the safety. So if I try to arm it...
Mode change to stabilize.
It won't arm.
Arm.
It requires
Fence
position.
requires position.
So if you don't have GPS, you're going to want to fly it in the cage without
Battery low.
GPS. So there's the arming checks, and right now we have them all
Transmitter battery low.
enabled. Let's see if we can charge this. That means if you don't have GPS locked, you can't take off. So what we can
Transmitter battery
do,
low.
charging. What we can do is the opposite, which is turn them all off. So how do I make that? 0. Now there's no checks. It will arm. It won't question you. So you can do this in the drone cage, or you can do it selectively. You can say, okay, I only want the barometer. So let me turn them all off. Write the parameters. And that thing means I'm ready to arm. It means I'm happy. And I usually have to reboot the flight controller when I do this.
Armed. Disarmed. Armed.
Now it'll arm.
Disarmed.
Okay.
Mode change to stabilize.
Armed.
Warning, arming checks disabled. Armed.
And now I can fly.
Warning, arming
If I had the
checks
props off, I
disabled.
could fly it around now. So
Disarmed.
be very careful when you change those arming checks. Please have them all enabled out at the arc. But when you're flying in the drone cage, you can disable GPS lock. But I would probably keep them all the other ones there. And assuming we have them all, that we do. The only thing we don't have is GPS, like battery level. So let's see if that's going to work. Right parameters. Yes. And now it doesn't want to.
Arm. Battery 1 below minimum arming voltage.
And
Arm.
battery voltage.
Fence requires
Oh,
position.
my battery is 6.2 volts. That's really low. I'm almost out of gas. That's like 5%. Okay. Well, want to be that way. Board voltage, battery level.
Arm. Fence requires position.
So I have to turn off
Arm.
the fence.
Fence requires position.
Geofence. Disabled. Right parameters. Yes. Ah, now he's ready to arm. Or she.
Armed.
Armed.
Okay.
Disarmed.
So you can adjust
Disarmed.
the arming parameters at will. Please use your discretion. If you have questions, ask me. And if you're in the cage and you're outside the cage, the worst that's going to happen, your drone's going to get crashed. But if you go out of the cage and you want to start playing around with the arming parameters, please be very careful. It's best just to leave them all on. Make sure you get GPS lock. Okay, so happy flying.